Hi everybody, it's Mrs. Mancuso. I want to do a video that goes through some redox reactions, but I already did like how to write out half reactions and how to balance it and make sure your oxidation number is going up and all that sort of stuff. Now what I want to do is I want to talk about electrochemical cells. And electrochemical cells are where redox reactions are occurring. And there are two types. There are voltaic cells and there are electrolytic cells. And they are each unique. Voltaic cells produce electricity. So we did a fruit battery lab where we used fruit and we actually used a voltmeter to measure how much electricity we were making. So this was a spontaneous reaction. And this had a conversion. And the conversion was we used a chemical reaction, so chemical energy converted into electrical energy. All right, an electrolytic cell requires energy. So usually you hook up a power source, something like a battery, for it to happen. It needs a battery because it's a non-spontaneous reaction. So it's a reaction that won't happen without an input of energy. And so the conversion here is you use electrical energy to make a chemical reaction happen. So the conversion is electrical to chemical. All right, and now I want to draw some pictures and show you a voltaic cell and then an electrolytic cell. So let's do voltaic first. So a voltaic cell, you have two separate containers or two separate cells. You have two metals and they're connected by a wire and there is a solution inside of here. Let's say this one is K and this one is Fe. So I have potassium on this side and I have iron on this side. And what I have to do first, I need a salt bridge. And the salt bridge, the function of that is to transfer ions. It'll become polarized, meaning there'll be too many ions on one side and missing on another side if you don't give them the chance to move back and forth. All right, so what I need to do first is I need to look up K and Fe and see which one's higher on table J. I know it's a spontaneous reaction, so the metal that's higher is oxidized. So there's K and there's Fe. So that means the metal being oxidized is K. So this is my ox. And I have a saying, an ox and red cat. So let's talk about what that means. There are two electrodes. The anode is the electrode where oxidation occurs. That's normally negative. And over here, the cathode is where reduction occurs. And the cathode, see that plus in the middle of it? Cathodes are usually positive. Now I remind myself, oxidation is losing, reduction is gaining. So now I show the loss of electrons. They would go through the wire from the anode to the cathode. And then I want to talk about what's happening to my metals. So over here, the potassium atoms are forming ions. So that means K plus atoms are going to form K plus ions in this solution. So I'm going to have a buildup of K plus ions. It means the mass of this is going to decrease. This, think of it like rusting. As this oxidizes, it basically is falling apart. So my oxidation half reaction would be K becomes K plus 1 by losing 1 electron. There is my half reaction. All right, over here, they would tell me the solution. So let's say it was FeNO3 2. So FeNO3 2 tells me the ions in here are Fe plus 2 ions. That's really important because actually if you look up Fe, there's multiple oxidation states. So Fe could be a plus 2 or it could be a plus 3. This is what lets me know what ion to start with. So it's an Fe plus 2 ion. Now I like to say my red cat gets fat. Over here I draw an arrow this way. That's showing my ions are forming atoms. And so they're going to clump onto this, and that's why this side is getting fat. It is gaining atoms. All right, so when I write my reduction, I follow the arrow. Fe plus 2 electrons becomes Fe. Now, if I had to write a balanced skeleton reaction, 1 electron is lost, 2 electrons are gained. So the common number that I need between them, I need it to get to 2. This one's already at 2, so I'm going to double everything on this side. So I would need 2 of the potassium atoms to be oxidized in order for 1 iron ion to become reduced. And then when I do the balanced skeletal reaction, 2 Ks plus Fe plus 2 become 2 Ks at plus 1 plus Fe. So this was my spontaneous reaction. I've got electrons moving through the wire. I've got potassium oxidizing and falling apart, and I've got iron forming on this side. So that's my voltaic cell. Now, an electrolytic cell. Electrolytic cells, remember, are not spontaneous. And the 2 basic types are either electrolysis, which means that you're going to split whatever it is, or plating. All right, so if you are splitting something, first of all, you just have 1 container, and you need to have 2 electrodes, and you need to have them connected to a battery. All right, so let's say I have CuCl2 solution inside of here. That CuCl2 could split into copper and chloride gas. All right, it's already balanced. Here it's a plus 2, here it's a minus 1. Now it's 0 and 0. So my metal is going down. That means my metal is reducing. My non-metal is going up. That means it's oxidizing. Over here on table J, I know that is totally not spontaneous. If I had a nice blue solution of copper chloride, I would never expect to form copper because that reaction is not spontaneous. So in order for this reaction to happen, you needed the battery to power it. The side that is positive is going to attract this negative Cl's, so I'm going to form Cl2 gas, the bubbles over here. And then Cu plus 2 is going to be attracted to the negative side, so this side is going to clump up and have copper on it. So the side that got fat, that's my red cat, so that's my cathode, and over here, this is my anode. And you'll notice the charges are the opposite when you have an electrolytic cell. When there's a battery, it reverses the charges. An anode still is oxidation, so it still is losing electrons. So I show the arrow going to the battery, and then I show it going to the cathode. And then if I write my half reactions, my oxidation over here, Cl2 at minus 1 became Cl2 plus 2 electrons. So I go from a negative 1 up to a 0. That's a change of 1 times 2 atoms is 2 electrons. And my reduction, Cu plus 2 plus 2 electrons, is going to form copper. So my copper is at my red cat, which is my reduction. And then plating, let's show that. Here's my container. Let's have like a spoon here. Oh my gosh, I can't draw. But there's a spoon, and that's connected. And let's say we have a chunk of gold. I want to plate my spoon in gold. And then here's my battery. So I'm going to label right away this as my red cat, because no matter what this is made of, I want to plate it. That means I want it to get fat. I want it to get covered in gold. So I know the arrow is going to go towards my fork. I want to oxidize my gold plate here, meaning I want to form gold ions. I want this to fall apart, form gold ions in the solution, and I want the gold ions to form atoms that attach here. So this is my anox. An anode is normally negative, but I'm going to put a plus sign here because I have a battery and it reverses the charge. My red cat would normally be positive, but because I have a battery, I want it to be negative. All right, my oxidation half reaction, I start with Au. There's my arrow. I form Au plus 1, and then plus I'm losing 1 electron in the process. So I'm going to show the electron going away from the anode and towards the cathode. So that's the pathway of my electrons. And then my reduction, here's my Au plus 1. I add 1 electron coming through the wire, and I form gold atoms, which is going to cover my spoon in gold. So both of these were non-spontaneous, both required a battery, both only had 1 container. All right, so there we go. There were voltaic and electrolytic cells.